All right, good morning. So this question is again on rotational motion, but the focus and emphasis of the question is on sliding motion. Okay. So before I talk about this question, don't forget to subscribe to this channel. I bring a lot of clarity in your mind, which will reduce your stress level. And due to reduction in stress level, you will be able to perform well in your exam because your mind will be calm, right? So don't get lost or feel frustrated because of physics. It's an easy subject. Watch my videos carefully and subscribe to the channel. Thank you very much. Let's go to the question now. So I was talking about a situation of sliding. Let's talk about it. Now this is again a ring. It is sliding down the inclined plane. The inclined plane has an angle theta. When I say the word sliding, what I mean is that there is kinetic friction. So this situation has no static friction. In the previous question, you saw the static friction at play providing torque. In this question, kinetic friction has come into picture now. Kinetic friction has different role than static friction in the case of sliding. Previous question was pure rolling. This question is sliding. Okay, I am not using the word slipping. Wait for it. So the question is focused on sliding. Question is what exactly is happening? I will tell you the exact question, but let's analyze. When kinetic friction is present, what happens? First of all, in sliding, when kinetic friction is present and the body is sliding, rotational motion is zero. No rotation. It is like a normal block which is sliding down, right? So even if this is a ring, this is just sliding down. It is only translational motion. It has no rotational motion, which means you will not create any torque-like equation in this. You will just create what? A translational motion equation, which is motion in a straight line kind of Newton's law. Second point, this point, which is a point of contact between the ring and the wedge, have no relative motion. Okay, they have no relative motion. Sorry, yeah, there is a relative motion. I'm sorry, they have relative motion. Unlike pure slipping, there was no relative motion. Here you have relative motion. When you have relative motion between the two surfaces, they slide over each other, and you have the concept of sliding there, right? Then what happens to energy? Because you have kinetic friction, you are bound to lose energy, right? You will lose energy. So the potential energy, which is at the height, as the body slides down, right, gaining kinetic energy, half mv square. There is no half I omega square because there is no rotational motion. So mgh, for example, here is 10 joules. You will lose some energy due to the friction. While coming down here, your kinetic energy here will be less than 10 joules, right? Because you are up against a non-conservative force, which is negative work, which will do negative work on you. So your 10 joules, you will do maybe minus 2 joules of negative work from friction, and your energy left is 8 joules. So potential energy is lost, and in the form of heat energy, and less kinetic energy is obtained here. Last, okay, now because I will talk about this later, okay, the sliding versus slipping, I will talk about it. Wait for it. We are just discussing sliding at the moment. Now the last point, what happens to acceleration of these circular bodies, or so to say the rigid bodies like sphere, ring, disc, as compared to the pure rolling? In the case of pure rolling, you're not losing any energy. So your acceleration is very good. You come back down with high acceleration. But in these cases, the acceleration is low. Why? Because you're losing energy, right? So you cannot gain that much acceleration. So if somebody says, what is the acceleration in pure rolling versus acceleration in pure sliding? The answer is in pure rolling, I will get more acceleration. Reason? I'm not losing any energy. In sliding, I will lose energy and therefore my acceleration will not be as high as in the case of pure rolling, right? Now let's talk about the equations. How do you write this? First of all, in these you're allowed to use mu k mg sine theta. Okay, this is your frictional force. Remember the frictional force in static case where you had pure rolling, you don't write it like this. You just write it like F static, right? F static reaches the highest value, which is the limiting value. You cannot write it as straight away mu k mg sine theta. That's not allowed in the pure rolling. In pure sliding, you're allowed to use this friction, right? So the frictional force which is acting here because of the relative motion is mu k mg sine theta, right? So mu k mg cos theta, right? Which is the normal reaction. So it is getting compressed and you have a normal reaction on it. So the frictional force can be written like this, right? Now the weight component, right, is this, which is mg sine theta, right? So there is an upward force, which is the frictional force. We have written this. This is upward. And this weight component is downward. We just need to write a sliding inclined plane question, right? So what do I write? I write mg sine theta minus mu k mg cos theta is equal to ma, and therefore the acceleration comes out to be g sine theta minus mu k g cos theta. That's your acceleration now. Period. Finished. Done. So sliding cases are very simple. Sliding cases are very, very simple, as you can see. Do you see that there is no mention of moment of inertia in this? Right? Because you don't have sufficient torque for pure rolling. You're sliding only. You have nothing with you that helps you rotate. In the case of pure rolling, you have something which provides you rotational motion. Here you have nothing that provides you rotational motion, right? So if you see, the moment of inertia has not come into play. So even if it is a ring or a sphere or a disc, you can see if the angle is same, the G is same, it's a kinetic friction is same for all the three or the four, then they will reach together because they have same acceleration. There is no difference in acceleration. The difference in acceleration can be produced, but they are different situations. We will discuss them when the moment of inertia also comes into play. And some rotational component is there and some translational component is there. Yes, I'm referring to slipping, but I will not solve slipping here. I'm just giving you a precursor to it as to what exactly are we talking about. We solved a situation of sliding motion. Sliding motion always has a kinetic friction. It is not pure rolling. Pure rolling has static friction. Please watch my previous video. So there is hell of a difference between pure rolling situations and sliding situations. Watch my playlist of rigid bodies. You will find some immense amount of wealth of information pertaining to the concept of the slipping and rotational and sliding, and numerous other questions on rotational dynamics, which will help you score very well in your examination. At least what they will do is give you practice. Go and watch that playlist. I will give you the link below. Okay. I hope you understood it properly and you liked it immensely. Please don't forget to subscribe to my channel, and I look forward to see you soon. Thank you very much for your time.